Today I want to talk about comparing SolidWorks bolt connectors with our theoretical expectations. Here we have two 1-inch thick steel plates that are bolted together by a 1/2 inch UNC grade 5 2.5 inch long bolt. The bolt is pre-tensioned, in other words, the nut has been screwed on and been tightened such that the bolt has been stretched by about 9,000 pounds. The way that's calculated, it comes from 3/4 of the proof strength times the tensile area, where for grade 5, the proof strength is 85 kpsi, and for the 1/2 inch UNC bolt, the tensile area is 0.1419 inches squared. We need the joint stiffness constant for this situation, and based on our theory, we know that the joint stiffness constant is a ratio of the bolt stiffness to the sum of the bolt stiffness and the member stiffness, and in this example, it's about 0.17. What we're interested in knowing is when we have this static external tensile force P applied to the members, what's going to happen? Well, actually, this is a statically indeterminate problem. Part of P is going to be carried by the bolt, and part of P is going to be carried by the members. And the way it's split up is actually based on the joint stiffness constant. So the part the bolt carries, P sub B, is about 0.17, or C times P. The part the member carries would be the remaining 1 minus C times P, or in this case about 0.83 or 83% of P. So the members carry a dominating part of that external force P. The force that's actually in the bolt is going to be C times P plus the pretension that we gave it initially. The force that's in the member is going to start with that compressive pretension that you put on the bolt, and then it's going to the 1 minus C times P is going to add to that. But it's important to know that the members will remain in compression. It's important that that happens, that the members remain in compression after the P has been applied. For factors of safety, the first one that we have is the yielding factor of safety. So that is actually going to be the proof strength divided by the stress that's in the bolt. And after you make your substitutions for these things, you can see that the yielding factor of safety actually never exceeds 1 1/3 based on how we've established our pretension of 3/4 times proof. A better factor of safety is actually the joint separation factor of safety. For this one, we're going to look at what the maximum P is that we could apply to the system, and that would happen when that would be the P that would cause the member force to actually equal 0. So it's really just Fi divided by 1 minus C. So when you take Fi divided by 1 minus C and then divide that by the actual P that's applied, that is a really good estimation of the factor of safety. That's saying how close you are to ripping this apart or getting the members to separate. Let's take a look at what the theory would tell us would happen as we apply that external load P. Here I've set myself up in Excel for a C of 0.169, where I've defined the variable C. I've got my pretension, Fi, at 9,000. I've got my tensile area at 0.1419. I've got my proof strength at 85 kpsi. And I've set myself up where I have P starting at 0 and then incrementing to 100, 500, etc., all the way up to about 11,000 pounds. And as you can see, I've got my bolt force here established as the pretension plus the joint stiffness constant times A11, which is the P, and then I take that and just increment it so that the current p-value for that row is being accessed. And as you can see, the bolt force starts at the pretension value of 9,000, which corresponds to a p of 0, and then in increments it gets bigger and bigger because some of the 17% or the c times whatever the p-value is being added to that pretension. Okay? Simultaneously with that, we want to take a look at what the member is doing. The member starts in compression with the minus 9,000, and that's 1 minus C times the current P minus the pretension of Fi. And as we load the member, as we apply the P, the member compressive force becomes less, and it goes towards 0. And where it goes to 0 is going to be about where P is about 10,800. So my P max is about 10,800, and that's going to give me where my joint separation factor safety is about 1. Notice I've also tallied up my yielding factors of safety here based on the proof strength divided by the current stress in the bolt, and you can see it starts at about 1.33 and then it diminishes. And of course my joint separation factor, since if P is 0, I'd be dividing by 0, so that's why I have that error there in the Excel sheet. But as I load the P, the joint separation factor safety goes towards 1. So that kind of sets us up for theory. Now let's take a look at what SolidWorks shows us. Okay, here I am in SolidWorks. I've created an assembly. I've got two of the plates that have been mated together so that the hole lines up and that the faces line up. Coincident? Then I created a static study. And in an assembly, of course, you are still worried about how you anchor. And what I did is I anchored the bottom edge of the bottom plate. You are worried about anchoring is important. And here I tried to avoid the hole of the nut. So I actually fixed the outer edge. And then for the external load, which is also important, I just put an external load around the perimeter of the top plate. That will be my P that I apply to the member. And again, I avoided the hole. Now, I haven't shown the bolt or the nut in this assembly, and you don't have to, it turns out. Okay, so for an assembly, of course, the mates really don't mean anything when you go do a static study. It's all about the bonding. So for bonding, let me go take a look. I'll show you what you have for bonding. And the bonding really talks about how the bodies that you have in your assembly, how they are able to either penetrate or not penetrate, or how they might be bonded. So you have three choices for bonding, and I've picked globally, I've picked allow penetration, which is normally what I do. What I did here to control what's actually happening between the two members is I turned on no penetration for the two faces where the two members are actually touching these two plates. So that's how I handle that, and that's how I normally handle it. Now, the thing with bolts that's interesting is I defined a connector, and let's go take a look at that. Edit definition of my connector. So this is a bolt connector, and there are 5 options. There's a standard or counter bore with nut. That's one option. There's a countersink with nut. I'm definitely not countersunk, so that's not it. Then there's a standard or counterbore screw, and that would be where the bottom member would be threaded. I'm not dealing with that because I would have a nut. And this is the same thing, countersunk with a screw, so the bottom member would be threaded. And this one would be where you actually have a stud poking out of the bottom member, so I don't have that. So the closest one I have is standard or counterbore with nut. And you can see here that I've already configured it. I've selected, here it wants the circular edge of the bolt head hole, which is what's highlighted. And then it wants the circular edge of the nut, a bolt nut hole, which is on the bottom, highlighted now. It wants to know what the bolt head diameter is, 3/4 of an inch here for a 1/2 inch bolt. And then my nominal shank diameter is 1/2 inch. Okay. Here are the materials I've picked. Here is the normal, it's one that I usually use in practice, A36 steel. And then here I put in the known tensile stress area of 0.149, 1419 inches squared. I put my S sub P, my proof strength is 85 kpsi, so I have that in. And then here, I know that the 900 inch-pounds of torque with the K of being 0.2, that's going to give me that 9,000 pounds of pretension. So I'm set there. And all those parameters are as you see them there. So that's how you set up a bolt connector in SolidWorks. And then, of course, you run it and mesh it the same kind of way. You've got the same meshing options you can go find. I just left it as standard for now. And then you can go and look at and I've set it up for Y stress. You can go take a look at the stresses, and I've taken a cut in the midplane so that you could see what it looks like, the truncated frustra here, and the blue showing that it's really in compression. Where the bolt head is and where the nut is, and then it's less compressive as you taper out. So that's looking kind of like we expected. Let's take a look at displacement. Same kind of thing. So here again we've anchored around the bottom perimeter, and we're applying remember the 1 pound force that we had there, which is effectively nothing. Green is 0, so we really have no displacement anywhere in here. The red here and the blue here is strictly from the pretension that we've put in of the 9,000 pounds. Let's go take a look at some of that. Let's take a look at the contact force that's going to be happening between these two members. So to see that, let me hide the top one so that I can pick that face and then update. So you can see here that we've got that 9,000 pounds, that from the pretension, that's what's acting right now on the members, the 9,000 pounds. So that's as expected. See if we can look at our bolt loads. So here the bolt force is 9,000 pounds from what we've set the pretension to be. So this all looks good. Okay. Now let's progress and look at what happens when we go to 100 pounds. So this setup now is effectively the same as what I had before. I've just changed the P to 100 pounds. Pretty much the same. So let's take a look at the stress. Stress kind of about the same. Displacement's kind of about the same. But let's take a look at the bolt force. Here, there doesn't seem to be any. I should have, if it were precise, I would have 9,017 here because I would be taking 17% of the C value times that 100 pounds. Right now I only have 9,000, so it's really not noticing that I've applied that at 100 pounds there. Let's take a look at what the force is that's interfacing between the two bodies. So I'm going to hide this one again and take a look at this force here. As you can see, it's now showing me 8,900, so it's looking like the members are accepting all of that 100 pounds, and that's not the way it really works. So something doesn't look right here. So that's 100. 500, let's go take a look at what we have for 500. Same thing again. Let's go look at the bolt, the contact force between the two members on this face. So for 500, again, it's put everything, is coming from the 9,000 compressive, and it's putting the 500 all on the members. So that doesn't look right. Let's take a look at what the pin bearing force is. Again, it's basically not having, it should have 9,000 plus 17% of 500, and it's still only showing the pretension value there. Let's go up to 1,000. List our bearing force. Still, effectively 9,000. I'm sorry, the bolt force. Effectively 9,000 there. That bolt force should be 9,000 plus 17% of 1,000, so it should be, what, 9,170, I guess. Let's take a look at what the resultant force is on that face. Contact, boom. So it's put all of that 1,000 pounds on the members. It's not right. Let's go up to 2,000 pounds. We'll start bearing our bolt force. Again, it's starting to accumulate a little bit, but it's basically still 9,000. It should be 9,000 plus 17% of 2,000. So that's not right. Let's go take a look at what the resultant or the contact force is between the two for 2,000. And is showing the 9,000 diminished by the 2,000. It's putting all of that 2,000 on the members. It's not right. Let's go to 5,000. Where's this resultant force? Contact. Let's put all of the 5,000 on the members, which has brought me down to 4,000 compressive. Let's take a look at the bolt force. Basically still 9,000. So it's not put any of it on the bolt. And let's go to 8,000. Let's jump ahead. The others are the same. Contact force now for 8,000. So that's left me with only 1,000 compressive left on the members. So this is not right. Let's put everything on the members. Let's see what the bolt force is. Basically 9,000. It should be 9,000 plus 17% of 8,000. It's nowhere near right here. It's looking wrong. Now for 9,000 here in SolidWorks, I wasn't able to put 9,000 because it effectively is blown apart here. But I put 8,975 is what I could put. So let's take a look at the resultant force. Contact. Boom, boom. So it's showing me with only 25 left because, again, 89.75. So it's put everything on the members. It's not what we expect. Let's see what the bolt says here. Basically 9,000. It should be 9,000 plus 17% of what the p-value is I had there. Okay. So as you can see, it doesn't look quite right. Let's see what our displacement looks like here. Let me show this guy. And you can see here that with the difference in colors there, the stark differences between blue and green, that the SolidWorks thinks it's moving there, that there's been some displacement. So it thinks the joint's been blown apart at this point, when it really shouldn't have been. It shouldn't have been blown apart until around 10,800. So that's what SolidWorks is showing us. It doesn't look like it's correct. When I go back and just kind of map what SolidWorks did, the tests I just showed you, and compare it with what we were kind of thinking theoretically over here, you can see that SolidWorks kept showing, no matter what P was, SolidWorks kept showing the bolt force at 9,000, but and then it was putting all of the P onto the members, diminishing it until we got to this point here. Another thing I wanted to show you is that SolidWorks actually does give you a factor of safety for the bolt. Here I'm in the P equals 0 example, and it's showing you that the factor of safety is about 1.33. So it looks like that is the yielding factor of safety that we had established before. And then as I load with the P, you can see that the 1.33 is still there, no matter what the P is. Go up to 1,000. 1.33. 2,000. 1.33. 7,000. 1.33, 8,000, 1.33, and then strangely enough, the 9,000, 1.33. As we know from theory, the yielding factor safety starts at 1.33 when P equals 0 and actually should be diminishing as P increases, particularly when we're getting up to such high value. The yielding factor safety goes towards 1. So this is definitely not right. The author tried a number of different combinations, for example, tight fit, different meshes, all kinds of different stuff, and even different versions of SolidWorks up to 2015. And the author was not able to get the theory of how the external load P is shared by the bolt and the members to agree with what SolidWorks provides. SolidWorks seems to say that the external load P is carried by the members only. Hope you've enjoyed today's presentation.